All right, now we'll move on to the next question. For students who need to review question 16, we have hydrogen and bromide. They usually do not react at room temperature and pressure, so we are not seeing any reaction. However, when it's being heated up to 100 degrees Celsius, we find that there is some form of reaction because we are seeing some hydrogen bromide being formed. And when you further increase to 300 degrees Celsius, then you'll find that the amount of hydrogen bromide formed increase even more significantly over the same period. So then the next part of the question is telling you that the amount of HBr increase further when you put in a platinum catalyst to the reaction mixture, which is already at high temperature of 300 degrees Celsius. So first part is asking you to write down the chemical equation with a balanced state symbols for the reaction. So the reactants in this question is hydrogen gas and bromine. So we need to put in the state symbol, and usually bromine in this case at 300 degrees will most probably be a gas because bromine has a low boiling point. So H2 and bromine as gas will form HBr, which will most likely to also be in a gaseous state because of its low boiling point. So to balance off the equation, we will have H2 plus Br2 to give you 2 HBr. Right? Okay. Part B. So they are asking you what could be a possible reason why there is no reaction at room temperature. So at room temperature, the particles may not have enough kinetic energy to overcome the activation energy for effective collision. So a possible reason is that the reactant particles do not So the reactant particles, they do not possess energy that's greater or equal to activation energy to allow effective collision. All right. So that's for part B. Next, using a Maxwell-Boltzmann distribution curve, explain why the amount of hydrogen bromide increases as reactant temperature increases. So you're expected to draw a Maxwell-Boltzmann distribution curve showing the effect of temperature. All right. So let's look at part C. So to draw a Maxwell-Boltzmann distribution curve, firstly, we need to label the axis correctly. So the axis on the y-axis label will be number of particles. Okay. Or you can put it as a fraction of particles, also possible. So it's number of particles for the y-axis. X-axis will be kinetic energy, or just energy will do, but I will prefer kinetic energy. All right. Now, the feature of a Maxwell-Boltzmann distribution curve is that it must start from the origin. Okay, so we have to draw a graph that starts from the origin, and it's not a nice, perfect Gaussian curve like this. It is not, okay, but it's a little bit skewed towards the taper. That means towards the high energy region, the graph is the area under graph is quite small. Okay, so it's not a symmetrical graph. So for example, something like this. Okay, so what are some of the points that we need to ensure? We need to ensure that the graph starts from the origin. There should be 0 particles with 0 kinetic energy. And towards the end here, we must ensure that the graph is approaching the x-axis kinetic energy, but never touching the x-axis. So it's approaching x-axis, but it does not touch the x-axis. So let's say this is our graph for 100 degrees Celsius. With higher temperature, we expect more particles to shift towards the higher energy region. And so the whole graph will be moving rightwards to the right. However, because the area under the graph, which is this portion here, remains unchanged because this portion area under the graph reflects the number of particles that we are looking at. And we are supposed to only change the temperature and not change the amount of reactant particles. So the area should be unchanged. So we move our graph to the right, keeping the total area the same. And so it will look something like this. So in this graph, in the red color graph is for 300 degrees Celsius, you'll see that it still starts from the origin. Okay, every point seems shifted to the right, and the tallest part of the graph, which is the highest probability of the particles with this amount of kinetic energy, that amount of energy has shifted to become higher, but overall the graph is now lower in height. And why is it lower in height? Because we need to maintain the total area under the graph same. So therefore the graph is shifted to the right with a lower magnitude in height. Okay? And so that's our graph, but we have not used it to explain yet. So in order to explain, what we will do is we specify an activation energy, and what we will do is we can shade the area under the graph. Okay. Now take note that the two graphs should only cross each other at one point, and that's it. So say for the 300 degrees graph, it should be approaching x-axis but never touching it, and the two graphs only intersect at one point. Okay, that you should not cross again one more time. And then this is the area under the graph. So if we look at my shaded region, purple and red shaded region, you will find that the red shaded region is larger. And the area under the graph that I'm shading represent the number of particles with E greater or equal to the activation energy. Okay, so when temperature increases, so we are expecting that there are more particles with higher kinetic energy. All right, so the area under the graph represents the number of particles with E greater or equals to EA. So the shaded under the shaded area Okay, so the shaded area represents the number of particles with E greater than or equal to EA. So we can see from the graph that there's more particles with E greater or equals to EA at 300 degrees. And with that, more particles meeting the minimum amount of energy required. So we will expect that the frequency, remember the frequency of effective collision increases. And therefore rate increases. Okay, let me highlight to you, you must use the word frequency. Frequency of effective collision, not the number of effective collision, because we're looking at rate, and rate has a time factor there. So we are seeing more particles with E greater or equals to activation energy, and we're therefore seeing an increase in the frequency of effective collision and leading to an increase in the rate of reaction. Okay, so that is for 300 degrees. All right, next, part D, very similar. They are asking for another Maxwell-Boltzmann distribution curve, but this time round is for catalysts. So you're supposed to use a Maxwell-Boltzmann distribution curve to illustrate how does a catalyst increase the rate of reaction. So again, the same thing. Let's sketch our Maxwell-Boltzmann distribution curve. All right, label the axis, number of particles. This part here will be kinetic energy. Now, for temperature, there'll be two graphs, right? Because they're representing 100 and 300 degrees. But for catalyst addition, it's just one similar graph, but the activation energy being shifted. So for catalyst, the rho is something that was added to provide an alternative pathway with lower EA, and as a result, it increases the rate of reaction without being chemically changed. So we first define what is a catalyst and understand that it actually provides an alternative pathway with a lower activation energy. So with that, it increases our rate of reaction, and the catalyst is usually regenerated without chemically being changed. So when we are plotting our Maxwell-Boltzmann graph, in this case, it will be a one graph. Okay, it will be one Maxwell-Boltzmann curve with an original activation energy, and this is the original activation energy and the area under it, and a lowered activation energy due to the effect of the catalyst. So EA cat will be lower in value than EA, and as a result of the lowering of the activation energy, we are seeing a greater shaded area under the graph, right? So how do we put that observation in our answer? How do we structure our answer? So we can state that catalyst lowers the activation energy, and therefore from the graph we are seeing that there are more particles with E greater or equals to EA. Okay, and you can see the shaded green area. So what will happen when you have more particles with E greater or equal to EA? Then the same thing, we always end off our kinetics question with the word frequency of effective collision. So every kinetics answer, we try to end off with this statement, frequency of effective collision increases, and therefore rate increases. Okay, so our catalyst lowers EA, more particles as depicted by the area under the graph, with E greater or equals to EA, and leading to an increased frequency of effective collision and a higher rate of reaction. All right, so that's part D, and the last one, part E. The reaction between HBr at 300 degrees is exothermic. So first key information from the question is that we are expecting an exothermic graph, exothermic reaction. And next is that we're supposed to sketch energy profile diagram, okay, for a catalyzed and an uncatalyzed reaction. So we need to make sure we remember how do we draw an energy profile diagram. So our energy profile diagram again has the axis. So we have to label our axis first. So we are expecting on the y-axis, don't mix up with the Maxwell-Boltzmann, please. On the y-axis is energy. And on the x-axis is not energy this time, then it's not time, it is the progress of reaction or reaction coordinate. Okay, progress of reaction. Okay, so if we put in the information, we are supposed to show an exothermic reaction. So let's sketch an exothermic graph whereby the reactants has higher energy than the product. The reactants have higher energy than the product, so the excess energy is given out. So if we sketch an energy profile diagram, it may look like this. All right, this is for an exothermic reaction. We have our reactants, our products, we have to label, okay, and delta H, or the enthalpy change, which is showing exothermic. Now, take note, since exothermic is negative, for chemistry, upwards arrow represent positive, endothermic, downwards arrow, negative, exothermic, there's no such thing as double-headed arrow, no such thing. So, since this is an exothermic reaction, I will have to draw the downwards arrow showing that there's energy release because the delta H is negative. All right. And to illustrate catalyzed and uncatalyzed reaction, I will often have to draw in the activation energy that is required. So therefore, is an upward arrow endothermic reaction, EA, uncat. Okay, this is my uncatalyzed EA. Then next, I will have to put in the catalyzed one. A catalyst lowers the rate of reaction, so I will have to bring down this part, which is called the transition state. So I have to bring down the energy of the transition state to somewhere here. Okay, so this is transition state. So with this, my reactant's energy did not change, product energy did not change, but just that the energy of the transition state is lower. And activation energy in the energy profile diagram is from reactant to transition state. So from the reactant to transition state, now I will draw an arrow, and that's the EA catalyzed. Okay? So EA catalyzed is less than EA uncatalyzed, and delta H remains unchanged when the catalyst is added into the system. So we are expecting to see two different peaks. Uncatalyzed peak is higher than catalyzed. The reaction must be exothermic, showing by a lower product than reactants and downward arrow. And then activation energy correctly labeled to show that activation energy with a catalyst is lower and is upwards arrow. And we need to label our reactant, products, and axis correctly. All right, so that's the energy profile diagram. All right, so after going through this, so it will be good to do some reflection and then recap on what you think is difficult in this topic and why. Is it the structure? Is it the way you phrase the questions? What are the areas that you are confident in, and what are some of the gaps in your understanding or gaps in the way you structured your answer? Okay, so we stop here for question 16.